All right, this is the Check for Understanding Module 16. You're asked to evaluate this line integral using Green's theorem. And so just a quick catch up here. You may have to go back to, I think it was the line integral part 2 video where I argue you need not parameterize a curve in order to compute a line integral. And it led to this pdx plus qdy interval. So I ask you over here to think, integral pdx plus qdy. If that's like you never heard of that before, then go back to module 15 and check out the second line integral video where I show where all of that comes from. So this integral is given to us in that form, and it is on a complete loop or an enclosed region. And so I just recognize the structure to be pdx plus qdy. Therefore, the vector field that we're in is the vector field 3x squared plus y squared I, the p component I, plus the q component j. Nice. So there's our vector field. We're traveling through this vector field along this curve, and we're asked to find the line integral. The whole idea of if we travel along that circle centered at A0, are we helped or hindered as we make one complete loop? All right, so first of all, it's going to be useful, I think I'm going to make an argument anyway, it's going to be useful to have this curve C parameterized, or not parameterized, but expressed in polar coordinates. So let me jump to Desmos and give you a little crash course on some polar coordinates. All right, here we go. So the first thing I have here is, because of some background knowledge I have, r equals a cosine theta is going to give me the circle shifted to the right a units. No, that's not even quite right. It's not shifted to the right a units. It's shifted to the right so that the edge of the circle is at a units, not the center of the circle. So to help convince you of that, notice I'm plotting the point a comma 0. Now, according to the setup of the problem that you saw in Canvas, a should be the center of this circle, not the one end over here at a comma 0 on the end of the circle, but should be the center of the circle. So I need to make some fixes. Also, just so you know, I've parameterize this Desmos in a sense so that it will build the circle, because I wanted you to see that it is going counterclockwise, which is a requirement for Green's theorem. Green's theorem requires that our complete enclosed region, doesn't have to be a circle, but our enclosed region has to be oriented in a counterclockwise fashion. You saw previously a square was a complete square, so a complete loop region oriented in that counterclockwise fashion. And so this indeed is just that. The issue I have right now is that A is not the center of the circle, but is the other edge of the circle. So I need to fix that. So to fix that, well, if I want A to be here instead of here, then I want this to just be 2A. That is, if I want the radius of my circle to be A, as shown in the picture in the problem statement, I want this to be the diameter, which would be 2A. So watch this. Bam. Let me bring this back so you can see it. And let me give you one complete loop there. There we go. Now, do you see it? Now I have A at point 8 at the center of the circle, and 2A is just the other edge of the circle, and 2A cosine theta does give me that circle shifted to the right or along the positive x-axis. By the way, if I change the cosine to a sine, it just puts the circle up oriented above on the y-axis. I hope that kind of makes some sense to you in terms of a crash course on some polar coordinates. So r equals 2A cosine theta. Keep that in mind as we move back to here. This circle is r equals 2A cosine theta. Lovely. All right, now you're ready for some Green's theorem. Green's theorem is a way to take a line integral situation. And remember, line integrals is this whole idea of dot product between the vector field vector and the path that we're on vector. And if those dot products are positive, there's an acute angle. If the dot product is 0, right angle. If the dot product is negative, we have an obtuse angle. And that tells us something about a context. But we can convert that whole setup into a double integral. And that just gives us another way, maybe an easier way than going through all the parameterization and dr/dt's and all that stuff. Maybe it would be easier to set up a double integral. Let's see. Keep in mind, Green's theorem only applies if you have a complete loop, oriented counterclockwise, all that jazz. So we do have that at least. Let's give it a shot. All right, so Green's theorem says, take the partial derivative of, now this is how I remember it, it's the partial derivative of the q component with respect to x minus the partial derivative of that p component with respect to y. That difference, dA, will be equivalent to doing all the original line integral stuff that you did with parameterization. Let's do it and see. All right, so we're going to do this thing. So I need some partial derivatives. Let's come over here and find dq dx. So here's q. Ah, man, it would be so much nicer if that was multiplied out. Let's do a quick rewrite of this thing. Let's distribute the 2x squared and get 2x squared plus 2x cubed yj. Just to make the differentiation a little bit easier. So dq dx, the derivative of this with respect to x is going to be 4x, 6x squared y. And then dp dy, the derivative of this, or this, with respect to y, 6x squared y. And so coming back to our Green's theorem, what we've got is the double integral over that region R, which is this is the region R we're speaking of. dq dx, 4x plus 6x squared y minus dp dy minus 6x squared y. And remember, this is all times dA. Nice. And now you can probably see why they set this one up the way they set it up, to kind of maybe showcase that Green's theorem can be useful, because it all boils down to just integrating 4x dA on that region R. All right, now, this is where I'm going to make an argument. In the video from MIT, they say, all right, now that we're here, let's find a way to integrate this thing so that computations are minimal. And the instructor approaches this from a center of mass argument. Making a center of mass argument, she's able to evaluate that integral without crazy, serious integration techniques. All right, that's great. I would like to approach it from a different angle. The angle I would like us to take is this. We have technology. So just like if I had at my disposal this experience with center of mass, I might go, hey, I could make a center of mass argument on this thing and integrate this thing with a minimal amount of computations. Well, likewise, I can make a technology argument here, and I can integrate this thing with a minimal amount of computations. However, either way, I've got to get the thing set up. I've got to employ some human thinking to get it to a place where if you know center of mass stuff, use center of mass stuff. If you know technology stuff, use technology stuff. But right now, or even up until right now, technology has not been helpful in terms of integration. It was a little helpful with Desmos, but in terms of integration, it's not helpful. So I still need to do some work to get to a point where technology is going to be my strategy as opposed to the center of mass argument. Okay, so set the center of mass argument aside. If you know that stuff and can apply it, great. I want to make a technology argument for evaluating this integral. All right, first, if I leave it in rectangular coordinates, my dA, this little bit of change in y and little bit of change in x, my dA would be something like this, except much, much, much smaller. My dA would be something like this. I would have to make a decision about, should I make it dx first or dy first? Let's just say I make it dy first. So y varies from here to here. y varies from the bottom of the circle to the top of the circle. Now, depending on what x is, my change in y is going to be either less or more or less. But I could say that this circle is centered at a comma 0 is x minus a squared plus y squared is equal to the radius squared. And then I could solve for y. I'm not going to do it now, but I want you to just get in your mind. If I solve this for y by subtracting the x minus a squared from both sides, take the square root of both sides, I'll get plus or minus some stuff. So I could make an argument that the dy would be the negative the square root of some stuff to positive the square root of some stuff. And then x varies from 0 to a to 2a. That would be fine. You can try to stick that into a technology and see what happens. Or you could convert this thing to polar coordinates, because from my previous r equals 2a cosine theta, that seems pretty good too. Let's go polar here for a minute. So in polar coordinates, I would have 4 times x. Remember, in polar coordinates, x equals r cosine theta. And then dA, remember in polar coordinates, dA is r dr d theta. And so here's my setup. I want to do dr first. R in polar coordinates is from the origin out to wherever you want to go. So r would be 0 to 2a, r would be 0 to something, r would be 0 to something, r would be 0 to something. What's the something in every case? Well, the something is r equals 2a cosine theta. So r is going to vary from 0 to 2a cosine theta, while theta varies from, oh, I think I missed this. Go back to the thing. Did I say this? I don't remember. But in this format, notice theta need only sweep out pi units. As theta varies from 0 to pi in this r equals, we get the full circle. And so back to my limits of integration, just 0 to pi. All right, so you see, now, just like if somebody has a center of mass knowledge, they can apply something. I had some polar coordinate knowledge. I can get it to this form, and once it's in this form, then I can jump to Wolfram Alpha. So I grabbed the widget for polar integral calculator. I put in the 4r cosine theta. The order was r dr d theta. R goes from 0 to 2a cosine theta. Theta goes from 0 to pi. Boom, boom, boom. There you go. 4 pi a cubed. That is the same result as what we saw in the video. Now, let me give you one more argument. 4 pi a cubed. Okay, now, suppose you wanted to go rectangular on this. You don't have the center of mass thing. You didn't think to go polar. You're going rectangular. And in rectangular coordinates, remember, y equals plus or minus the square root of a squared minus x minus a squared. And so the negative y would be the bottom half of the circle. The positive y would be the top half of the circle. And this thing would set up, let me show it to you. We're going to integrate for x. We're going to have x going from 0 to 2a. Remember the 0 to 2a to get all the way across the diameter of that circle. Y is going to go from negative the square root to positive the square root. And so that's exactly what I want as my input, but standard computation time exceeded. So there you go. That's my argument is I don't have the center of mass technique. I have technology. But technology and polar and rectangular coordinates brought me to a standard computation time exceeded place. Bam! So, given my experience, hope yours too, that we have polar coordinates at our disposal, polar coordinates led me to a beautiful result of 4 pi a cubed. I wanted you to see that you could also perform one round of integration here. Notice this is 4r squared cosine theta. And if we integrate with respect to r, we get 4/3 r cubed. Do your fundamental theorem of calculus. you might want to pause the video and see it, but you get this result, which Wolfram alpha will confirm as well. The integral of 32a cubed thirds cosine to the fourth x from 0 to pi, check it out, 4 pi a cubed. So again, it's, to me anyway, it's more of a, hey, what tools do I have at my disposal? In our case, more technological tools, because it is the year 2020, come on. So, but even with technological tools, we may make decisions about how much work we're going to do or not do. Like, I can just stop at the polar coordinate deal and get 4 pi a cubed. I can do one round of integration that's not that crazy and just use Wolfram alpha for this single variable integral. I could use rectangular coordinates, but rectangular coordinates kind of cause some trouble in this case. So I needed another tool. All right, that's all I have for this. I hope that helps.